Okay, in this lesson, we're going to go ahead and look at two ideas. One is compound events, and the other thing is probability given a certain situation. So first of all, let's start with compound events. Imagine an urn with four marbles, two red, one green, and one white. So what I'm going to try and get at is how would we find the probability of first pulling a green marble out and then a red? How would we calculate that? Well, and this assumes if we pull the green marble out, we put it back in, and then the next marble we pull is a red. So what's the probability of that happening? Well, first of all, let's go ahead and look at a tree. So here I have the first draw, red, red, green, or white. And the reason I did two reds, I'm just trying to show the two red marbles. So we have equal probabilities here. And then I draw my second marble. If I draw a red the first time, I still have all four marbles available for the second draw because I put it back. Same thing here, here, and here. So including the dupes, because some of these look very similar, how many outcomes do I have here? Well, there are 16 of them. And that kind of makes sense because you say, oh, 4 choices for the first and definitely 4 for the third, for the second choice, so 4 times 4 is 16. Now, how many of these marbles had a green, how many of these outcomes had a green marble first and a red marble second? You can see over here there are 2, and that comes from getting the green first and one of these reds. So either one of these 2 work. So there are 2 outcomes. Well, what's the probability that we draw a green marble on the first draw? Well, that would be 1 out of 4 because there are 4 marbles in there and only one of them is green. What's the probability we'll draw a red on the second draw? Well, you can see in all these situations, here it's 2 out of 4, there it's 2 out of 4, there it's 2 out of 4, and there it's 2 out of 4. So it's basically 1/2. Now, if I asked you what's the probability of drawing a green and then a red marble, we had 2 outcomes out of 16, which simplifies to 1/8. But what happens if I just multiply this probability times that probability? Oh, I get the same answer. So instead of having to do a tree, I can do a shortcut and just multiply the probability of the first thing happening times the probability of the second thing happening, and I get 1/8. All right, so let's go ahead and now instead of putting the marble back, we're going to keep it. So I have to get rid of some of these outcomes where I kept the marble. All right. And so now how many total outcomes do I have? You're going to see that there are only 12 total outcomes because I have 4 options for the first round and 3 every time for the second. So how many outcomes had a green marble and then a red marble? It was just the 2. Right? So the probability of drawing a green and then a red is 2 out of 12. Notice this changed. It used to be 2 out of 16. Now it's 2 out of 12, which is 1/6. Well, did the probability for drawing a green marble on the first try, did that change? No, it's still 1 out of 4. But how about the probability of getting a red marble? Well, you're going to see that it kind of depends on the second try here. Here, it's 1 out of 3. Here, it's 1 out of 3. Here, it's 2 out of 3, and it's 2 out of 3 there. What did it depend on? Well, it depended on which marble I pulled the first time. So how do I show that? This is the probability of getting red given that I got a green. So here, given that I got a green, how many ways could I get red? 2 out of 3. So that probability is 2/3. So the probability of getting a green and then red marble, we said, was 1 out of 6. Does it work if I multiply these 2? Well, you'll get 2 over 12. Guess what? That's 1/6. So you can, even if you do without replacement and you have these probabilities changing here, as long as you adjust that probability for the situation, it works out fine. So again, before, in the previous example, the probability for red on the second marble was always 1/2 because we put the marble back, it didn't affect it. Now the probability depends on what came first, in this case, green. If I had said probability of red then red, my calculation probably would have been a little bit different, okay, in terms of, the probabilities here and here. Okay, So this brings us to independent versus dependent events. If A and B are independent, then the probability of B does not affect A. In other words, the probability of pulling a green marble on the first one doesn't affect the getting a red marble in the second. And we would say, oh, it's just the probability of drawing red in general. Okay, same thing here. So, but when you do without replacement, in the second situation where we kept the marble, we found out that the probability actually does depend, and so that is called dependent. So which one of these are dependent? Well, if I replace it, I'm not changing the probability the second time, so that's independent. Die, if I roll a die and draw a card, they don't talk to each other. That's independent. Drawing 2 marbles from an urn, well, that's what we just did, and if I kept both of them, that one actually is dependent. And then rolling a die twice, the die doesn't affect, the first roll doesn't affect the second, so that's independent. Over here, which one is the dependent one? Well, if I roll a die and flipping a coin, that's not it, all right? Drawing a card and flipping a coin, those don't affect each other at all. Flipping a coin twice, it doesn't remember what the first flip is, so it doesn't matter. D, drawing 2 cards and keeping them from a deck does affect it. So this brings up the multiplication rule of probability, basically, which is the main point of this first part of the lesson. Probability of A and B, A and then B, is just take the probability of A times the probability of B. It's also true for dependent events. The only thing you have to do is tweak this probability to take into account how the probability changed because A happened. Kind of like when we kept the marble, how did the probability of red change if I got a green? So let's do some quick examples. We've got some batters here for the Round Rock Express. Here are their real batting averages. And are the probabilities of getting hits dependent or independent? Well, if they're good professional baseball players, you'd hope that their probabilities are pretty constant. So we would say it's independent. They shouldn't be affecting each other. So if I'm looking at the first place, the first 2 batters for the third inning are Carlos and Tomas, right? So he's got an amazing batting average, and Tomas has not a bad one. That's actually not bad, .33 or 330. But I'm looking at the probability that he gets a hit, which is going to be more than half the time, and he doesn't. So the probability he doesn't get a hit is also going to be more than half the time, right? Because it's not this number, it's the opposite. So it's going to be 0.667 times 1 minus 0.33. So it's 0.667 times 0.67, or 0.440. Now, the first 2 batters for the 9th inning are Hanser Alberto and Kyle Blank. So what's the probability both of them get a hit? Well, Hanser gets a hit about 1/3 of the time, and so does Kyle. So we just multiply both those probabilities together, and voila, about 10% of the time, almost, they both get a hit. So what's the probability of rolling an odd number on a die, assume a 6-sided die, normal one, and flipping heads on a coin? Well, we'll just take the probability of getting an odd times the probability of getting heads. What's the probability you'll get an odd? Well, that's 3/6, and heads is 1/2. Multiply them together, and you get 1/4. They're independent. The outcome on the die does not affect the coin flip. Now, when I did an earlier lesson, we looked at the probability of spinning a purple 6 times in a row. And what was the probability of that actually happening? So I actually did spin purple 6 times in a row. How often should I expect that to happen? Well, I'm just going to go 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times. So 1 for each spin. And I get 1/64, or about 1.5%. So 1.6 almost. So it's pretty rare. I'd have to play that with that manipulative about 64 times, roughly, not exactly, predicted to get purple 6 times in a row. All right, let's go ahead and now, so that was the first part of the lesson, that we learned that when you have probability of something happening and then something else happening, that you multiply the 2 together. All right, now we're going to look at a different probability, which is the given probability. And let me go ahead, we're going to revisit our cats and our dogs. So first of all, what is the probability a student likes dogs given that they like cats? Well, given means that we are only looking at people who like cats. Where are they? There they are, right? Those are the people who like cats, normal people like me. And then there are crazy people who don't like cats. But anyways, all right. So how many of those people like dogs? 15 out of 18. So that's your probability, about 83%. Is the probability that a student likes dogs if you know they already like cats, at least in this survey. What is the probability a student likes cats given they like dogs? So am I still looking at the yellow group of people? No, I'm actually looking at this group of people. Those are the people that like dogs. And what's the probability they like cats if they like dogs? Well, there are 15 of those people who like both. And it would be 15 out of those 20 people, or 75%. All right. TJ has a 65% probability of making the first shot in a free throw. And by the way, I guessed on these, and she said, actually, you're pretty close. So she knows her free throw percentages. So if she makes the first shot, then she has a 90% probability of making the second shot. Why is that? Well, first of all, you're always more likely to make the second shot because you can make adjustments after the first shot. And if you made the first shot, you're like, oh, I don't have to adjust anything. I did it right. So you're going to get it most of the time unless you somehow, accidentally change too much. Now, if you miss the first shot, you still have a better shot at the second shot because you also get to make an adjustment there if you need to do it. So first of all, let's look at the situation where she makes 2 shots in a row. That means she has a 65% of the time we expect her to make the first shot. We're only looking at those, right? So we take that 65%, and then she makes the shot. What's the probability she'll make the next shot? It's 90%. We just multiply both those numbers in decimal form. Don't do the percent. And you get roughly just under 60%. And that kind of makes sense because if she did 100 shots, you'd expect her to make 65 of the first 100 shots and almost all of those on the second shot. You see how that works? So what's the probability she misses both shots? Well, that would be, we know that she makes a shot most of the time the first time, so when would she miss it? About 35% of the time. And which condition would we be talking about here? Well, she didn't make the first shot, so I would ignore this 90%. If she misses the first shot, we say, well, she's going to make the second shot still about 3/4 of the time. So how much of the time will she even miss that one? 25%. So we're going to do the 35% from the 65 times the 25%, which is a complement of the 75%. And we say, oh, about almost 9% of the time she will miss both shots.